Hello and welcome to Eng Phys 3 BA3 Binary Math and Counters. Binary Math Addition Registers. A register of two-state flops is a natural storage container for binary numbers. We've got two states, so we're going to store binary, two possible states numbers in them. So just a reminder, a binary number looks like this. Each place tells you the number of that many powers of 2's. So this is 2 to the 0, 1, 2, 3, 4, 5, 6, 7. So this number here means that we've got 1, 2 to the 7, 1, 2 to the 6, a 2 to the 3, and a 2 to the 1 added together. So that's 128 plus 64 plus 8 plus 2, or 202 in total. It works the exact same as our regular decimal numbers do, so except for 2's instead of 10's powers. So this is 8 10 to the 0 plus 9 10 to the 1 plus 3 times 10 to the 2, 4 times 10 to the 3, 1 times 10 to the 4. So this is something that you don't even think about anymore when you're dealing with powers of 10. For binary, it's exactly the same, just as with powers of 2. If you want to convert this back to a decimal number, it looks a little bit, it's a little bit clunky to do. But as long as you stay just within binary, then the math works out exactly the same as you're dealing with for decimal numbers, except that there's no such thing as 2. The standard computer representation is to have registers that have multiples of 8 places. So this would be an 8-bit register. There's 8 little digits in here called bits. A byte is 8 bits, so this would be a 1-byte register if we have this many stored in there. There's larger registers, but they're always in multiples of bytes, or multiples of 8 bits. Let's look at binary addition. If you wanted to add 1001 to 0101, then let's do this. We get 1 plus 1 is 0, carry the 1. And so we've got 0 plus that carried 1 is a 1. 0 plus 1 is 1. 1 plus 0 is 1. And there we go. That's our result. Let's check this by converting the numbers to decimal. So let's see. That would be 1 plus 8 is 9. And this number 1 plus 4 is 5. 9 plus 5 should be equal to 14. And what do we have here? We've got 8 plus 4 is 12 plus another 2, 14. So 9 plus 5 is 14. It worked. Okay, how did this, let's look at the detail of how this worked. We've got a 1 plus a 1, and then we could get either a 0 or a 1 for adding any two bits together. In this case, 1 plus 1, we get 0, carry a 1. And so the rules for any addition of 2 bits are as follows, and you could probably figure this out anyway. 0 plus 0 is 0, carry the 0. 0 plus 1 is 1, don't have anything to carry. Same with 1 plus 0, but 1 plus 1, we get 0, carry the 1. Now, when we added up this next set of numbers, we needed to also consider the carry that was coming from the previous bit. So in general, we want to also be able to add numbers by carrying a bit in. So here's how this works. This is like a 3 bit adder. We can add the 2 bits that we're concerned with, but then also the carry bit from the previous bit. So we've got, at most, 1 plus 1 plus 1 is a 1, but then we're also carrying a 1 over, so we don't have to add like 2 different kinds of carries. We just have 3 in and then 2 out. The regular out for that same position, and then the carry out. How could we implement this? Well, here's a way to do it with gates. We've got some exclusive ORs here, some AND gates and an OR gate, and then this does exactly the addition that we're looking at. So then this is not the only way to implement addition with gates. It's just one way that you can trace and see that it works. Okay, so give that a shot. Unsigned and signed numbers. These are ways to represent positives and negatives. So if we have, here's a list of counting up, like the bits from 0 up to 1111, so 0000 to 1111. Now the way we've been talking about this, we've been talking about unsigned representations where 1110 was 14, like we had in that example before. The signed representation does something a little bit different to allow us to represent negative numbers, and it's a bit surprising. What we do is we take the most significant bit spot. So for 4 bits, that would be the 4th one, and we say that that's not 2 to the 3 or 8 anymore. This is now negative whatever it was going to be. So negative 8. This looks a bit strange, but it means that when we add 1 to it, we're always counting up. It always increases the number by 1. So from 1001, if we add 1, we get 1010, which means either 9 plus 1 is 10, if this was an unsigned number, or it means -7 plus 1 is -6. Either way it works. And so the point of using this, the advantage of using this notation for negatives, where this means -8, is that it lets us use the same addition architecture as for unsigned numbers. So for whether we've got negative numbers or positive numbers, we can use these exact same circuits to add the numbers together. And then it's just up to the programmer to decide and realize whether the number was a signed number or unsigned number at the end of it. Now, one thing to note is that the overflow happens in different positions. So if we were to add this with the number 1, so 1111 plus 1, then the unsigned interpretation is that causes an overflow, because it would give us a 0, 0, 0, 0, 0, and we'd carry a 1 out of that. Maybe we don't do anything with that carry bit. And the unsigned interpretation says that 15 plus 1 is 0, 0, 0, 0, 0. 15 plus 1 is 0. Well, that caused an overflow, meaning that we went over the limit we were supposed to and looped back down to a number that probably isn't what we wanted. Now, in unsigned numbers, though, in signed numbers rather, in 2's complement, let's look at what it says. It says -1 plus 1 is 0. Well, that's right. There's nothing wrong with that. So the overflow didn't happen in that spot. On the other hand, look at what's going on here in the middle between -8 and -7. If we take 0, 1, 1, 1 and we add 1 to it, then we get 1, 0, 0, 0, which for the unsigned interpretation says 7 plus 1 is 8, no problem there. But for the signed interpretation says 7 plus 1 is -8. That's wrong. We've got an overflow happening. So the overflows happen in different spots in 2's complement versus unsigned. Okay, next up, binary multiplication. Rules of binary multiplication are the same as you might expect for addition. So what this says is that 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. How you actually implement multiplication is by shifting and adding. So we looked at some shifting in registers in the last section, and that's another math operation that you can do, is shift bits around. So it's kind of a fast thing to do from a computational perspective. So here's how we'll multiply this number by this number. What we'll do is this 1 here means we'll leave the top number alone, 101, and then we'll add it to 0 times it shifted 1 spot, which is this row, and then add that to 1 times it shifted 2 spots, this row, and then 1 times it shifted 1, 2, 3 spots, which is this row. Adding all of these together, we've got 1, 0, 1 and 1 is a 0, carry the 1. We get 1 and 1, 0, carry the 1, 1 and 1, 0, carry the 1, 1 and 1, 0, carry the 1 to there. And that's our result for multiplying these two numbers. That's how you do it. For division, we're just going to need fractions. So to represent fractions in binary, a bit n places to the right of a decimal means 2 to the negative n. So 0.01, if we were to write a binary number with this point in it, I guess we can't really call it a decimal anymore because it's not, what would you call it? Maybe a biennial. Yeah, dec means 10. So this might be point. Maybe this is like 0 biennial 01. Let's just say point. That sounds kind of awkward. Anyway, this means 2 to the power of -2, right? So if it was 1 over, that would mean 2 to the power of -1. So 0.01 in binary means a quarter. Okay, so let's see. We've got 1 divided by 1, 1, or 1 divided by 3, and we're going to work out what this is. So let's see, how many times does 1, 1 go into 1? Does it fit? No, it goes 0 times. So now let's go 1 spot to the right. How many times does it fit in 1, 0? 0 times. Okay, well, let's go 1 more spot to the right. How many times does it fit in 100? It's smaller than that. Okay, so it fits 1 time in. So we take 1 times this, and there's our 1, 1. We'll subtract this number and this number. So this 100 minus this number here, and we get 1. And now, does it fit in there? No, but if we go 2 spots over, multiply it by that, we've got the 1 down there again. Subtract these numbers, 100. And does it fit in there? Nope, go 2 numbers over, 1 times that, 1, and subtract to get another 1. We could do this forever. So we've got a repeating decimal. A third in binary is, 1 divided by 3, and we get 0.01 repeating. Now that's maybe not surprising. A third is a repeating decimal in base 10 as well. But one thing that's important to note is that numbers that are terminating in base 10 often are repeating in binary. So it's possible to perfectly represent the number 0.1 in base 10, but in binary that turns out to be an infinitely repeating decimal. So this is a source of numerical error. One problem that with binary numbers is that they take up a lot of space. So here the number 15 is 1111, which takes up a lot more, twice as many digits as it did in decimal. So we could just use decimal numbers, but the problem with using decimal numbers is that it's kind of awkward to translate them between binary and back. One nice system that translates well to binary, because it's a multiple of 2, is a base 16 system, and this is a popular thing in computers, a hexadecimal system. So we need, rather than base 10 where we go 1, 2, 3, 4, 5, 6, 7, 8, 9, we need to go, we need to have 16 different symbols. So we've got 0 as well, and that's why there's 10 different symbols in base 10. There's just 0, 1, 2 symbols in binary. So for base 16, we're going to need 16 different symbols. We've got 0 to 9, that's 10 of them, but then we need some more symbols to go up to number 15, and we use A, B, C, D, E, F. That's the most popular way to do it in hexadecimal. So one thing that's nice about it is because because it's a multiple of 2, it's 16, we've got that every digit in hexadecimal corresponds to exactly 4 digits in binary. If you were to write in an octal system, because 8 is 2 to the power of 3, then every digit in octal would represent 3 digits in binary. Because registers are typically multiples of bytes, so multiples of 8 bits, then the hexadecimal system is a bit more popular than the octal system. So let's look at this. We've got FF. We can just look at each piece of it separately. F maps to 1111, and then F maps to 1111. So that means FF maps to 11111111. This is 255. FA1E would map to 1111, and then A, which is 1010, 10001, and E 1110. Okay. So it makes conversions quite a lot easier than they are to convert to decimal. Let's check out what these numbers were. FF, as mentioned, is 255, so that's 15 times 16 to the 1, plus 15 times 16 to the 0, 255. And FA1E would be 15 times 16 to the 3, plus A is 10 times 16 squared, plus 1 times 16, plus E, which is 14. So 64030. Okay, let's give some practice to this. What's the sum of two hex numbers, A34 plus 5BF, and then find out what the answer is in hex and in decimal. Okay, let's just leave them in hex for adding them. So we've got 4 plus F. F is the last digit, so this is going to wrap around and give us a 3, and then we carry the 1. So we've got B plus 3. B plus 3, we can imagine, well, we're new to this system, so let's just count on our fingers there. We're going to add 3 to B, so B, C, D, E. And then with the carried 1, we get to F. And now we've got A plus 5, so that's A, B, C, D, E, F. So we get back to F, and we're left with FF3 as the answer. 15 times 16 squared, plus 15 times 16, plus 3, just to add it all up, is 4083. Alternatively, we could have converted each of these numbers to decimal and then added that. How about 45A times 4? Well, this is a bit tricky to do if you leave it in hex. You can convert both numbers to decimal and then just multiply them if you want. In hex, let's stretch our computer muscles here and try and calculate this out. So A times 4, A is a 10, that's 40. And how many 16s go into 40? 2 of them. So we're carrying a 2, and the remainder of that is 40 minus 32, which is 8. Okay, now 4 times 5 is 20, which has 1 16 in it, remainder 4, and then plus the 2 that we carried is a 6. 4 times 4 is 16, which in, let's see, so, and we carried a 1 over, right? Yeah, we carried a 1 over, so 16 is just like a, well, we get a carried 1 and then a 0 plus the 1 that we carried, and that's why it's 1168. Okay, so in decimal that was 1 times 16 cubed plus 1 times 16 squared plus 6 times 16 plus 8 is 4456. All right, next section, counters in sequential logic and timing diagrams. This thing is a ripple counter. What does it do? Well, the circles on the clock input mean that it triggers on a negative clock. We've got a bunch of JK flip-flops which are going to flip their output state because they're all wired high. So whenever we trigger these flip-flops, they're just going to swap whatever they were on. So let's look at the first one here. We've got a clock input and it triggers on falling clock. That's what the circle means. So, okay, clock goes down, and then the first one, if it was a 1, it's going to go to 0. And then when the clock goes back up, it stays 0. When the clock goes down, it's going to trigger and swap. So it goes from 0 to 1 because both the J and K are high. Okay, and then clock goes back up, it stays there. Clock goes down, it goes back to 0. So that's what this is going to do. As the clock goes down, up, down, up, down. On each down, it's just going to switch from 0 to 1 and back and forth. Okay, now this output is the trigger for this next JK flip-flop. So when the output first goes down, then this flip-flop's going to flop down as well. And it's not until then this one goes back up, this flip-flop ignores it, and when that goes down again, this triggers and goes to the opposite, and so on. And so the next flip-flop, the third one, is going to wait until the second one, until Q1, that is, goes down to swap. And then the fourth one is going to wait until Q2, the third one, goes down. So when this goes down, that goes down, and then it stays there until this one goes down. So what is this doing? Well, it's counting, right? So we've got 0, 0, 0, 0, 0, and then like counting, if we take this as the most significant bit, it's like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, and so on. So this setup of flip-flops is just counting because it kind of ripples from one to the next to the next. It's called a ripple counter. In fact, these you can tell that what would really happen is there's some time for the signal change to propagate through each flip-flop. So after the clock pulses, even though we've drawn it as if the clock pulses down and then this goes down immediately after, in fact, this would go down some small amount of time later based on the slew rate of these flip-flops. That's how long it takes for them to transition once they've been told to. So if the signal takes a little bit of time to fall down, let's imagine 5 milliseconds, then this one will fall down 5 milliseconds after that, and this will fall 5 milliseconds after that, this will fall 5 milliseconds after that. So in fact, this is going to kind of ripple its changes through like ba 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 ba. That's what a ripple sounds like. Right. You maybe can picture like those old-timey clock radios that would sort of flip over their numbers like one to the next to the next to the next. Anybody remember that? All right. All right, the last chip that we're going to be concerned with is the 555 timer. This is what the 555 timer looks like. It's not actually a timer by itself. It's only a timer when you put it in another circuit. So first, let's look at what this chip does by itself. It's got a couple of inputs. It's got threshold and trigger, and reset. Let's just pretend that reset is pinned high so that we're not worrying about what that does. It's like it's not even there. Now, if you forget to hook up reset or you set it to ground, then that's going to be causing some havoc in your circuit perhaps, so make sure to pin that high. This is really the don't reset button. So as long as you're giving that a high, then it's going to keep not resetting. All right, the output is taken from the inverse of the Q bar output. These circles mean inverse, so inverse of the Q bar output of this flop. So it's like it's taken from the Q output. Let's look at these things. These are op amps without feedback, so they're just comparators. The circles don't indicate that we're inverting this. It's just showing you the negative input. This thing, because there's no current that can go into the op amps, is just a 3 resistor voltage divider. So we've got VDD over 3 here, and 2/3 of VDD here. So let's see, when are we going to be hitting these set and reset inputs? This one, reset, is going to be triggered if threshold ever goes above 2/3 VDD. Then we're going to be sending, okay, positive is bigger than the negative input, so we send out a 1, which is going to hit reset. This one's, we're going to set the set bit if trigger is ever lower than 1/3 of VDD. So we compare threshold being bigger than 2/3 VDD and trigger being lower than 1/3 VDD. All right, let's look at what's going on here. So we've got this circuit set up like this. We've got VS, a resistor, another resistor, capacitor to ground. Threshold and trigger are tied together, and we've got this other discharge thing that we didn't really talk about. First, let's imagine the capacitor is not charged initially, so we apply VS, and so this starts charging up. There's no current that can flow into threshold or trigger, actually, because they go into op amps. So we're eventually going to be charging the capacitor up. Now what happens? So as we start, when it's initially uncharged, threshold and trigger are both 0. So this one says, well, 1/3 of VDD is higher than 0. So the set bit is set, which is putting out, which means we're forcing this flop to output a 1. And that means that the Q bar output is a 0. And so the actual output is a 1. This thing, which we didn't talk about yet, is an N-channel Mosfet. You can tell it's N-channel because the arrow is pointing towards the direction the majority charge carriers would go if we put a positive charge there. So that means they're negative. So the majority charge, the things that we would fill up the channel with, are N. So if we put the set bit on, then this is a 0, and so this is not turned on, and discharge is not connected. Okay, so discharge is just sort of floating. It's not connected to ground. So we can ignore this pin. So we're charging this up, charging up the capacitor, building up the voltage. What's the first thing that happens? So eventually, as the voltage increases across this capacitor towards VS, then trigger goes above 1/3 of VDD. And then this op amp turns off, and we're not setting the set bit anymore, but because we're not setting the reset bit yet, and then this latch, this flop or latch, it's probably a flop inside the circuit, but we're using it as a latch anyway. This just keeps the same output, right? We're not setting the set bit, we're not setting the reset bit, so this just holds what it was, which was outputting a Q equals 1 or a Q bar equals 0. Now the next thing that happens, eventually we're building up the charge even more, so we get to the level where where threshold rather, is above 2/3 of VDD. That's the next thing that happens. When threshold gets above 2/3 VDD, then we set the reset bit, which now makes the output go to a 0, so the inverted output goes to a 1, and actual output goes to 0. Inverted output goes to 1, which means now we turn on this MOSFET and we connect discharge to ground. So we started off with 0, we start charging it up, and we're outputting a 1 this whole time. Then we get to 2/3 of the way up, and this becomes grounded, which now means the capacitor is going to start discharging this way. Once it gets, so the reset, even though we drop below that level immediately, so we stop being at 2/3, stop threshold from being at above 2/3 of VDD, because this is a latch, it just holds that output value. So we still discharge, keep discharging, and until we drop below 1/3 again at trigger. So this capacitor charges up, and the output is a 1 until we get to 2/3 of VDD here, and then it starts discharging until we get down to below 1/3 VDD, and then it starts charging until we get to 2/3 VDD, and then starts discharging until we get to 1/3 VDD. So the output is going to be 1, then 0, then 1, then 0, then 1, then 0, and keep regularly swapping between those with a 50% duty cycle, so meaning that it's up for the same amount of time as it is down. And the timing that it gets set with is based on the RC time constants. Now actually, since the way that it's drawn here, just for arbitrary R1 and R2, it's got a different resistance in its RC time constant on the way up than it does on the way down, it's not going to have the same duty cycle on the way up and down. You can make the timer behave differently in either of those directions by choosing the right kind of resistor and capacitor ratios. The values of these set the frequency. So if you make it charge up and down really fast, then you can make a fast timer. If you make one that goes slowly, then you can make a much longer timer. This is what you're going to be using in the labs. First exercise for the end of this section, make a timing diagram for this ripple counter we looked at, similar to the one that we made before, but instead now imagine that the output Q0 is initially low instead of high. Show that this doesn't actually affect the property of the circuit to act as a counter. We're just sort of starting at a different position in the counting. Really do it. Give it a shot. Like really, these circuits are kind of confusing, and it just takes time, spending time thinking about it to figure out how it works. Okay, well, looking at how this works, this was initially low, so when we swap this down, it's going to go high. On the next clock pulse down, it's going to go low, and the next clock pulse down, it's going to go high, and then you draw that all the way for this one. And then once you've got this timing diagram, you can draw this one's timing diagram similarly for that. So all in all, looks like this. It's almost the same as the previous one, except we start at number 1110, and then switch to 1111 before we finally switch to 0000, and then continue as we had before. Okay, this is a pretty difficult one. Design a counter to divide an input clock frequency by 7 instead of a multiple of 2. So the ripple counter, if we were to just take the output of this, we'd be dividing the clock frequency by 2, yeah? If we took the output from this one, it divides the clock frequency by 4. The output from this one divides it by 8, and the output from this one would divide it by 16. But how could we get it to divide by 7 instead of a multiple of 2? Well, the hint is to use AND functions and test for the bits in the number you want and generate a reset through the S inputs of a 3-flop counter register. To avoid the problems, the reset command should come on the following clock trigger, not instantaneously. Otherwise, the case of short slewing time, in that case, the reset would try to force the output state to a value inconsistent with itself, so that's no good. This means that you should add an additional flop to issue a reset command to the counter. Sketch the timing diagram for the circuit after you've designed it. Now I suggest that rather than, the sketch should be a check, but the easiest way to do this is to probably start with the timing diagram. You need to return to the starting state on the 7th clock interval. So so you start on 000, 001, 010, 011, 100, 101, 111. You need to get back to the last state and then flip back down to 0. So if you still want it to start at starting state 111, then you can make it flip back down to 0 after that. So this is going to be a thing that will set all the bits to 111 as soon as we get to number 5. All right. So here's how we're going to do it. We've got our flip-flops here. They're hooked up almost the same as before, except now we've got a test. We've got a 3-input AND gate that says, is the output number 5? If so, then on the next clock down pulse, force everything to go to 1 by setting their set bits. All right, so that takes us to 111, and then we're going to ripple back down to 0 on the next one. Great.